One issue you face when trying to put an old PC together is choosing a sound card. It can be difficult, if not impossible, to find one with all the features you want, and compromises often have to be made. Still, we can get round this a little bit by hooking up the system speaker to, well, just about any sound card with some pretty simple circuitry, and we'll look into how to make that today and how it works. Hello everyone, I'm High Treason, and, well, yeah, I've just told you what we're going to do. As usual, I've been faffing about on the second channel, playing a bunch of games nobody gives a damn about, but feel free to have a look at it. But on this channel today, we will be hooking up the PC speaker to sound cards that don't have the PC speaker connector, and well, we can hook just about any audio source up to this thing. It's not a complicated device, very easy to make, and I figured, yeah, why not? I made one, so why not talk about it, because I've not really seen anybody else prattling about with this. Somebody will have done somewhere. It's too simple to not already exist, but I've just not seen it, so I figured I might as well cover it. We'll get on with that, but if my voice sounds a bit off in this one, I've got strep throat or something going on. I've not recovered from it yet, so I'm probably going to sound a little bit strange through this one. But I don't stop for nothing, so, well, yeah, here we go. Let's get on with it. If you've ever tried to hook that PC speaker header on your motherboard up to one of the analog inputs on a sound card, you probably found that either nothing happened or, worse, the wires started to melt and no sound came out anywhere. Even if it did somehow work, those inputs are usually stereo and that output is mono. In reality, the two things have got nothing in common other than the style of the connector they use, which in hindsight might not have been the best choice, and we can thank Sony for that, so well, that figures. Actually, that's unusual. Sony using the same connector as something else. Usually they've got their own special, unique crap. But bashing overpriced wanky companies aside, just about everything on the sound card, especially the analog stereo inputs, are, well, analog stereo inputs at line level, which is to say that AC signals at around 0.7 volts peak to peak, carrying minuscule amounts of current. There have been different connectors with different pinouts over the years, but the signals are almost always the same, or close enough, being a left channel, a right channel, and some sort of ground reference that you don't really need because it's part of the same system. The PC speaker, on the other hand, is a digital signal from the programmable interval timer. It is at TTL levels, which is to say 0 volts or 5 volts with nothing in between. Technically there will be transients because, well, transistors don't turn on instantly, and if you want to go down the rabbit hole, the speaker can't change position instantly either, which does have some uses, but we're not really bothered with that today, and we're getting distracted. Sort of. Time is actually an interesting constant in electronics, and one that's quite easy to overlook or horrifically miscalculate, but we shouldn't have any issues with that in here today. On most motherboards, one pin of the speaker header is connected directly to the 5V DC power rail. The other pin is connected to the programmable interval timer, and different motherboards have different ideas about the exact wiring, but in any case you're relying on a transistor somewhere. When the relevant timer on the interval timer isn't in use, that didn't really flow very nicely off the tongue, the transistor is turned off and current cannot flow through the speaker. When the timer is set to trigger periodically, the transistor will turn on for the duration of that period and let current flow through the speaker, then turn off again for the same duration. This is to say we get a pulse with a 50% duty cycle, or a square wave. It's a simple enough sound as there's no envelope for amplitude or anything, but it's good enough for beeps and blips, and it was certainly adequate for the business-oriented tasks early PCs tended to be lumped with doing. Even worked well enough in a lot of older games for upwards of a decade. On many boards, simply tapping the pin hooked up to the transistor will do nothing, because, it turns out, a far few are implemented as open collector. That is to say, the pin is always at 0 volts, and can only selectively sync current to ground from somewhere else. It can't source it. Older boards do seem to flirt the pin up to 5 volts more often, and so it may be possible to tap just that one pin, but there's really no standard for how it was done, or even which pin is which, nor whether the 2 pins in the middle do anything at all. It's quite easy to solve anyway, as well the fix for it will work on either implementation about the same, so we'll just assume here that it's an open collector board. Here's what we can do. We want to get the buzzer signal and hook it up to something, say the auxiliary or CD header on a sound card. The circuitry for this is really quite simple, and we could probably get away with a resistor divider. You might have to play with the values, but this will work. R1 will limit the current, and R2 will divide down the voltage to levels the sound card expects. I don't know, there's plenty of resistor divider calculators out there, it's really down to you. I like to use a 1K resistor to limit the current and then fiddle around with R2 to really fine tune it, because it's a bit different from one machine to the other. The type of connection we've made to the sound card is technically wrong because it's DC coupled, and you'll probably hear quite a lot of noise from the power rail and the motherboard logic, but if you don't care about that sort of thing, or intend to just mute that input in the sound card's mixer when you're not using it, it might be good enough. We can improve it slightly by putting a capacitor between the divider and the sound card, which equates to AC coupling. Now only AC can flow from the cable to the sound card. Technically it's still DC, sort of, but it isn't like the components have any other reference to know any differently. Incidentally, some sound cards AC couple their headers anyway, having the series capacitors on board. It doesn't really do any harm if you have more than one capacitor in series, but they do have some amount of resistance. They'll attenuate your signal, and the total capacitance of the series will be less than the sum of all the capacitors making it up. The formula for which is really rather like that of resistor dividers, strangely enough. Still, one rather mind-bending thought is that if you started stringing capacitors together, the total capacitance of the series would get lower and lower, eventually approaching infinity, and yet it wouldn't ever reach it, surely, you would think, would it? I don't know. What do you reckon? Either way, having a capacitor in series as a method for AC coupling should work. It's tried and tested, and it's what most audio equipment does. In fact, it will exist somewhere on the sound card already for something that it does somewhere. There is a slight problem. We don't have an auxiliary header on this sound card and only have the one CD header, which we could certainly use, but then we won't be able to plug in the optical drive's audio signals. You could tie the wires together here, but this will also be tying the left and right channels together, making your CD audio mono. Not really great. I mean, we paid for CDs to have that super high-fidelity stereo audio, didn't we? And this is a bit of a waste. Now, usually we could employ passive mixing using some resistors here, but we'll get crosstalk through them. Now, you might remember something quite key to us having to mess about with circuits in the first place. The speaker's actually driven by a TTL signal. We can just drive more transistors with it. Our circuit will technically be a digital buffer, I guess, but could be considered a really, really poor amplifier, to the point that it's actually an attenuator, as the signals that come out of it are kind of weaker than the ones going into it. It doesn't really matter what you want to call it, because its main job is isolating the signal. Firstly, we want to put a resistor across the PC speaker's pins to account for motherboards which are open collector, as we have to get the 5 volts from somewhere if we're going to switch anything. On boards where the signal pin floats to 5 volts on its own, this resistor won't be needed, but including it isn't going to do any harm. Another resistor should be placed between the signal pin and a capacitor. You might have to fiddle with the values for these, but I found a 1K resistor and a 0.22 microfarad capacitor works quite well, and it's what I had in, so it bloody ought to. If you notice low frequency pulses aren't getting through though, you could try using a larger capacitor, maybe a 1 microfarad. We point this capacitor at the base of a transistor, an NPN in this case, but it wouldn't be very hard to adapt this circuit to use PNP. From the base we'll want another resistor pointing towards ground. I use a 100k resistor for this. It allows current to flow in reverse so the capacitor can discharge while the timer is off. The transistor also has some parasitic capacitance, but people never seem to mention this. It's very much worth remembering, as it can cause very strange things to happen in circuitry if you're not aware of it. From 5 volts we make a resistor divider like before, but this time it's between 5 volts DC and ground. The centre of the divider should connect to the transistor's collector. The transistor's emitter also needs to point towards ground. From the collector we can take a capacitor and point that towards another resistor. I use 470 ohm resistors for this, which is connected to the sound card's input. We can now parallel another resistor, another 470, for any other inputs, in this case the CD-ROM drive. That's the left channel. For the right channel, we just build the same circuit again. As signals cannot readily cross from one transistor to the other, we effectively eliminate crosstalk and can now hear the CD-ROM in stereo, despite having the mono buzzer signal plugged into the same place. The resistive mixing employed will reduce the power of the signals somewhat though, so you'll most likely have to crank up the input on your sound card's mixer a little. Some sound cards don't have any form of internal inputs at all, like the Sound Blaster 1.5 or the Adlib. We could modify the sound card, but, well, we can just as easily work around the problem because the sound card's output is just another analog audio signal. From a wiring standpoint, we essentially just substitute the CD audio with the sound card's output in our circuit. We can add more sources if we want to, just by adding more resistors. You'll notice the lack of AC coupling capacitors for these sources in my schematic, which is purely because pretty much all of these devices already AC couple their outputs with capacitors, but you can of course add them in if you want to. It's not going to do any harm, really. You could also substitute the pull-down resistor of the dividers in the buzzer signal there to make the volume adjustable for them. Of course, you'd have to adjust it for each channel, so you probably want something with a VU meter on it to try and match them. I just do it by ear. If it sounds fine to me, then it's fine, is my way of doing audio. Our circuit here does have its own quirk though, which is signal bias. When the buzzer fires, it will momentarily bias the audio signal into the negatives. This is actually fun because it highlights something people often neglect to understand about electricity. Many a time I've observed people think of voltages as absolutes, but they are entirely relative. It probably occurred to you that we'll actually see the same phenomena without AC-coupled transistor base, and that's why we need that resistor pointing up from ground there. Yeah, so some of you probably thought that was a pull-down resistor, but it's a pull-up resistor in that moment, isn't it? It's both. In any case, our transistor will settle out to being off when the timer isn't firing off pulses, so the only way things can go when pulses arrive is to bias the audio output downwards as the transistor turns on. It will take a few pulses before it settles out and swings either side of 0 volts, relative to whatever you've got this thing plugged into, of course. As the programmable interval timer signal is resting at 5 volts, the initial part of the pulse dragging this to 0 volts will actually be missed entirely, as the transistor's already off, and it can't be biased more off than it already is. We can negate this bias somewhat by causing more bias. In this case, we use a voltage divider on the transistor's base, probably flirting it at about the halfway point, say 2.5 volts relative to whatever ground is. The exact values you need will have to be selected based on the gain of your transistor and the resistors used on its collector. Now, when the programmable interval timer isn't running, the transistor's still trying to flow some amount of current. It's a little wasteful, but it's quite negligible. When the PIT signal goes low, the transistor flows less current and swings the output signal upwards. Then, as the PIT goes high again, the audio signal will swing downwards, as it was before, but now the signal should be fairly well centred if you picked out the right resistor values. Do remember that silicon transistors have a threshold of about 0.7 volts and a voltage drop of about 0.7 volts, so, well, you might need to account for this when you're messing about with the values of things in the circuitry. I don't believe it's too critical in this circuit, as, well, it's a digital signal and the fidelity isn't great. As long as there's enough room to swing either side, the thing should work. As it is, because the signal is a digital square, I didn't think it was worth implementing this here, but it is worth being aware of these principles anyway. They do tend to come in handy, especially if you want to build, like, say, a single rail amplifier one day. I use them in my audio replicator, Sour Mix, to deal with having an operational amplifier running on only a single rail. Yeah, this whole contraption handles AC in and out despite running from a single 12-volt DC source. You just biasing it halfway and AC coupling it. It's quite simple. There's not really very much involved in doing it. As it happens, my printed version of the PIT pump also resorts to this method for the speaker outputs. Being limited to very little current on a single 5-volt DC supply, it's not going to go very loud, it's prone to distorting, and I certainly wouldn't want to listen to my tunes through it for any length of time, but it will at least drive the chassis speaker. It was mostly implemented just so that beeps can still be heard if nothing's plugged into the rear output. I wasn't going to put in a lot of time into devising a good circuit for driving a tiny 1/4 watt 2 1/4 inch speaker encased in a metal box, sorry. Thanks to audio jacks coming in the switched varieties, you could always rely on a switched internal header to run something more elaborate if you wanted to. The circuits on this thing really are very, very crude, but that means you can and should definitely make your own one if you can. The AC97 output, for example, requires nothing more than a connector being added. We talked about amplifiers, and if you made your own pittance pump on stripboard, there'd be nothing to stop you just using a different amplifier than this crappy single transistor. You could have like a TEA 2025 or a TDA 1517, or even make your own amplifier out of individual transistors to get ridiculously loud outputs and have it pretty much brick the power supply as soon as the bass hits. One of the main reasons I opted not to add an amplifier was because I wanted to keep the board small and cheap and very simple and not introduce noise anywhere. People neglect to remember that transistors actually do make noise, and so the more of them you have, the more noise you have to try and negate. If I chose an amplifier solution for the circuit, someone somewhere would think it was the wrong one and want to use a different one, and I'd rather just use an external one, or for the most part rely on the capture card's input on my K5 and I'm listening through my headphones. But whatever the case may be, I had fun coming up with this thing, and maybe someone somewhere might have learned something about electronics or found some inspiration for an idea in there. Somewhere. I don't know how that's possible, but you might have done it. Certainly I'd like to hear about it if you make something similar, as you really could go quite far with this idea and make something completely ridiculous if you wanted to. But it's kind of my approach to electronics, is to use as few components as possible and have the simplest thing you can without losing the basic functionality. And I feel I achieved what I set out to do with this one. I'm quite happy with it. It works. Well, there we go. I think that really is about it for this one. This thing works. It's functional. You've seen I've made these printed boards, and you're probably somebody wondering, am I going to sell those? I've got about 10 of them that I will sell. I probably won't make any more, and unless there's a lot of demand for it, but really I think you should make your own, because they're very easy to make. There's no specialised components on there. You could buy those components for next to nothing, and you could almost certainly just steal them out of something that isn't working anymore. They're all very standard off-the-shelf parts, and you've got a full schematic of it to go on, so it might be a fun thing to try.
Just make sure you don't blow up the sound card. It's not too easy to do, but yeah, it helps to really test things with your multimeter before you start plugging them in if you're not quite sure. And obviously the motherboard logic, you want to be careful not to mess something up. But unless you really short something out somewhere, there's not a whole lot that can happen for the most part. You know, if you know what you're doing with electronics, there's nothing really that complicated in here. Even a fairly novice hobbyist should be able to make something like this. What sort of limitations this thing has, I don't really know. It's a simple enough device. There's quite a lot of leeway in it. Yeah, of course it can be improved upon. I'd like to hear about it if you improve it, if you build something ridiculously overblown or find a way to simplify it further. I'd like to know about it. I'd be curious. You know, it's always interesting to see what people can come up with. But I think that really is all there is for this one. As usual, I don't know what we'll be doing next, because I don't really make plans, because they never work out. So, well, I guess it's kind of a cold ending on this one, because I'm High Treason. Thanks for watching. And until next time, remember, don't be a screw-up. Lord DOS 622 up.